The second method, the formulation of it is very similar to the false position method, which was a bracketing method. And in there we were using a lower bound and upper bound, again two values. And as you can see, if you compare these, they are very, very close to each other. That's why a comparison between them is valuable. So this is basically an open method, while this is a bracketing method. And the difference between them is that in the open method we don't use we use two estimates, but we don't get them as the bounds or as two ranges, and the root stays in between. But in the bracketing method, the root should stay between the lower and upper x estimates. So let's see that here. In a new iteration, two replacements are xi plus 1 is replaced by xi, and xi is replaced by xi minus 1. So you can see here, for instance, we have the root, and xi is here, xi is here. So simply we need to get the derivative. The derivative is here actually, and xr is the point that we predicted. Then we use this function value and get the next derivative like this, and it takes us to here. Then we will get the function value again. Then from here, the previous one, this one, we are getting the derivative. So always the I plus 1 is replaced by I. That's important from iteration 1 to iteration 2. And as a result, the two values can sometimes lie on the same side of the root. So they can be on the same side, no problem. So the root is here, but the x values are on the same side. For certain cases, this can lead to divergence too, because the Newton-Raphson also is diverging with the real derivative value, and this can have some vulnerability of divergence. In the bracketing method, on the other hand, the root is always bracketing the root. The root is here. In here again, we are having a linear line between these and choose this value. But in this case now, we need to have another u value which will make this based on this formulation somewhere here. It has to bracket it again. So it is bracketing it again, as you can see. And because of the bracketing, it comes closer to the point very, very, very well. So this is very similar to this. The difference of bracketing the root makes this to converge to the root much faster. And that's why the method always converges, because the root is kept within the bracket. This is important. So there can be divergence here, but this will always actually capture the root because it's bracketing. These are the differences between second and false position. And let's compare the results of second and false position method for a problem, example 6.7. In here we have this function ln x, and we want to predict its root starting from xl is x minus 1 equals 0.5, and xu is x0 5.0. Actually this is not here, but let's remove this. It's minus 1 below it, under it, like minus 1. So when we use xl and xu, we will use false position. When we say x1 minus 1 and x0, that means second. And let's recall the functions, they are similar to each other. And for second, we have I and I minus 1. For false position, a bracketing u and l. And these function values are bracketing the root for both of them, but it doesn't have to be for second. We just use the same values to compare them. In the false position, we have 3 iterations, and in each of those, if you remember, false position was keeping one line like constant, one side. There's a one-sided issue here, but it's going to the root. False position method is convergent for this example. It's going to the root, which is nice. It's keeping it like this. But in the second method, you can see after, even in the second iteration, it's diverging. It's going to the minus values. So we want the value of 1 actually. The true value is 1. but here it's not diverging, so it's diverging for this example. That's why we can, when we use second, it's dangerous. We can have divergence, but in the false position we can have convergence because it brackets the root. This was a simple example. You can simply solve these to get these values. I'm not going to solve them, but you can have hand practice by writing these down for all iterations and see the results. In this slide, we will compare all the bracketing and open methods that we learned so far. If you remember, for the bracketing methods, we learned bisection and false position. For the open methods, we learned secant, Newton-Raphson. Of course, there is fixed point iteration as well, but that's the simplest version and that can have large errors. So we just want to compare only the Newton-Raphson and secant. So let's investigate this. You can see, first of all, errors get lower more quickly for open methods. So you can see that the errors are like quickly going down for secant and Newton-Raphson. That means if a root is being estimated like with a convergence, for example, for this function, it's converging to a value for all of these. And if it is converging for secant and Newton-Raphson, they are going much faster than the bracketing methods. Second, the secant method has larger errors than Newton-Raphson. So if we compare the open methods, secant has a larger error, slightly larger than Newton-Raphson, as you can see. And because the finite difference estimate of the derivative, and we are using a real derivative value for Newton-Raphson, that's why it's very accurate. But in secant, we have an estimate for it. That's why it can be less accurate, as you can see. But still, it's very good actually. It's very near. And this difference is the just derivative estimation difference. Third, although the secant method may be divergent, when it converges, it does so quicker than the false position. So false position is a bracketing method. If secant, because secant has an estimation of derivative, that means we are trying to find the path using the derivative. And if we use derivative, it is always faster than not using the derivative. False position doesn't use the derivative. That's why secant, if it is converging, it converges faster than false position. That's the advantage. And false position is inferior to open methods because one end stays fixed to the bracket of the root. So yeah, you remember that it has one-sided issue. Maybe modified false position should be used to get a better estimation. But secant and Newton-Raphson, the open methods, are better than the false position, better than the bracketing methods in terms of converging quickly. If they converge quickly. This property is an advantage to prevent divergence though. So the false position has bracketing of the root, and this is a good advantage because it is always converging, prevents diverging. But secant and Newton, because they don't bracket the root, they can diverge. But it slows down its rate of convergence. The bracketing has advantage of reaching or converging to the root, but it can be slower, especially bisection. Bisection always there is no way of not reaching to the root. It's always reaching to the root because it's bracketing always. But it is too small. You can see too slow. Sorry, you can see that it's going slowly. So has the slowest rate bisection because it is the simplest bracketing method, but it converges for sure to the root. These are the comparisons of open and bracketing methods. You can make similar comparisons, similar interpretations when we use different methods in your exams, in your practices for the predicting the roots, let's say.